So we have these two basic definitions now, E of theta and I of theta, and we've defined theta as well. And we anticipate that if we can find these functions, we might be a step closer to designing our reactor. So let's think about how we could develop methods for determining E and I. And before we do that, let's just think about what those might look like in some of our reactor types, some of the reactor types we are already familiar with. So let's consider our CSTR, our perfectly mixed reactor. And of course the characteristic of the perfectly mixed reactor is that the concentration is the same at all points in that reactor. And more than that, it's that whatever enters is instantly homogenized with everything in that reactor. So it also means that if you take a sample at any point in that reactor, you will get the identical type of fluid as you would get at any other point, including a point at the exit. So a characteristic then is that the concentration that you get anywhere in the reactor is the same as the concentration at the exit point. And this also applies to age distributions. So if we were to take a sample in the reactor, we might see a certain age distribution there. So we can call this maybe just a dash to distinguish it. This is an internal age distribution of a specific sub-volume in that reactor. Then we've got some collection of particles in there, and we'll get a certain age distribution at that point. And according to the CSTR model, we will get the exact same age distribution in the exit stream here. So if we were to plot E of theta, we'll get the exact same type of distribution. And I'm not drawing the correct distribution here. We'll see that that takes a very specific shape. But just as an example, the characteristic of the CSTR is that we've got the same age distribution inside the reactor as in the exit stream. What that also tells us is that the probability of any fluid element exiting the reactor is completely independent of the nature of that fluid element. So it doesn't matter how long something has been in that reactor, it has the same probability of exiting as anything else. And if we think about what that means, we can see that that actually relates to the type of distribution function that we'll get. So if we think about our young fluid elements here, so if we think about fluid elements that have just entered the reactor, then those fluid elements have the same probability of exiting, of appearing at the exit point, as any other fluid element, right? Any fluid element that has been there for a longer period of time. The difference being that there has been more opportunity for these other fluid elements to exit than these ones. So in terms of the individual event of exiting, there's an equal probability of these ones exiting, but they have been here a shorter period of time. So they haven't, if you like to think of those as discrete events, they haven't had exposure to as many exit events as the other older fluid elements in the reactor. So it's less likely that those fluid elements would exit. And what that makes us think then is there will probably be more of the younger fluid elements than the older fluid elements in the reactor, and so perhaps the distribution looks something like this. And I've focused on the younger fluid elements, but maybe thinking from the older fluid element side, it is harder to survive to greater ages in this reactor because you are constantly subjected to the possibility of exiting here. So the younger fluid elements have a greater probability of being in that reactor than the older ones. And you can take an analogy with people crossing a road. So if you have a road where cars are passing through, and people are also entering and exiting from this road at random, and let's say people are running back and forth across this road, then someone who has just started this questionable activity, that person might be able to make it across the road and still be alive to make a return try. But the more you keep doing that, the less likely you are to make it across. So that's the same analogy as here. It's unlikely that you will make it to these much greater ages, and so the number of fluid elements of those greater ages drops off as we increase in age here. So this is the expected curve for us for the CSTR. Now let's think about the other extremum. Remember, this is an extreme case. This is perfect mixing. It's saying anything that comes in instantaneously mixes with everything else. So that's an extremum. Now let's think about another case. Let's say we have instead the plug flow reactor. So if our fluid is in plug flow, then this is the opposite case. This is where everything is staying together in one plug that's chugging along, and so everything that comes in stays together as a plug. We don't have diffusion ahead of or behind. There's no dispersion of this plug of fluid. It's just flowing. Everything stays together, flows along, and then it all exits in one go at the exit here. So that's plug flow. And if we think about this, you've got all your fluid elements entering, and it's age 0 here. So your fluid elements at this end of the reactor, that's age 0 by definition. It hasn't spent any time aging there. So that's age 0. And then if you look further down the tube at another position here, then that will have some other age. So that won't be age 0, that's some other finite age, and all the fluid elements here will have spent some other time, and so on. So you'll reach the exit. So all the fluid at this exit point will have the same age. So they will all have the specific age associated with this point. And you can actually calculate what that might be, right? If we know the linear velocity of the fluid through this pipeline, and if we know the distance here, right, just call that L, then we can say tau, let's let tau be the time spent going from the entry to the exit point. We can work out tau just by taking the distance divided by the velocity. So that must be the time taken by all fluid elements to reach that exit point. So in this case, we can think of the exit age distribution E of theta as looking like this. It will be 0 everywhere except for at this point tau, and then we'll have everything at that instant tau, and afterwards we will have nothing. So there's nothing at the exit point with an age greater than tau, and there's nothing at the exit point of an age less than tau. We only have fluid elements of age exactly tau at the exit point. So we'll talk about what function we can use to represent this later. But for now, we can say we expect a distribution like this. And just to soften it a bit, let's just draw it as a peak for now. It's not quite correct, but we'll say all of our fluid elements have the same age theta. We have none of ages less than theta or more than theta. So it looks like a sudden spike here. So that's E of theta. So at the exit point, that's the age distribution we can expect to see. Now let's look at the reactor itself. So we can see that we have ages in this reactor of age less than tau. So we don't have fluid elements here of age greater than tau, but less than tau, we can think of there being equal amounts of the different ages there. So if we were to take the same age interval, let's say we took 1 second intervals, then you can say that closer to the entry point, we've got these young fluid elements, and then looking a bit older, we've got certain older fluid elements, and so on. So we can see equal proportions of these different ages up till age tau. So our internal age distribution, in this case I of theta, we expect to look something like this. So if that's tau, then we will have equal amounts of all those fluid elements until age tau, where we'll get 0. So afterwards we have none of those fluid elements. Before that we have equal amounts. So that's what we expect to see in terms of the plug flow reactor. So we do have these two extrema. We've got this perfectly mixed case, and we've got this perfectly not mixed case, this plug flow case, and we've got some indication, just using our physical intuition, we have some expectation that our age distribution is going to look a certain way. So now let's think of a way to actually calculate that or measure that.